Hello, my name is Vetle Vinje. I work for CGG, and I will present a new seismic acquisition system where we shoot over the seismic spread. This has been done in close cooperation between CGG and Lundin, so we have authors from both of these companies on this paper. So back in 2016, when we launched this idea and this technique on the Norwegian oil conference, this was the image that the artist company did on the concept. At that time, we had been working for 2 or 3 years with the concept, testing a lot of stuff, trying all conceivable problems and issues, but it hadn't been tried in full scale. Well, fast forward 1 year, we are in the Barents Sea. This is September 2017, and here is the drone photo of the acquisition, where you can see the streamer, the source vessel with its 3 sources shooting on top of the streamers that are 40-50 meters beneath the sea level. And you have the streamer boat far in front. So we have 3 sources spreading them far out. In order to describe and give a background on why we came up with this, you need to go back to the history of the seismic acquisition. It's in the marine acquisition. It started in the end of the 60s in a very simple way with 1 streamer, 1 source, 2D seismic. And then as the years progressed, as you can see here from that orange arrow, we went to more and more streamers, from 1 streamer to 2 streamers in the 80s, up to the 12, 16 and even 20 streamers we have today. Also the number of sources were increased from 1 source to 2 sources to up to 3 or even 5 sources today. And the quality of images has improved enormously, like the one on the lower left there from my textbook in the 80s, which shows an image at that time compared to a more modern high definition broadband image from today. It's been a journey from very sparse, low density acquisition on the left with 1 cable to today's ultra-modern, ultra-dense acquisitions on the right, which are also much more effective and efficient. But one drawback with this way of acquiring data is shown here. Here is a typical modern wide tow marine seismic, and it's more than 1 kilometer wide, as you can see from those arrows. And this is a 300 meter offset class coverage from that sail line. We add another sail line and another sail line, and they also have their own coverages, but there is a huge gap in between. It's several hundred meters wide. So the modern marine acquisition is very efficient, but it's lacking the near offsets. That is a drawback. As you can see on the lower right there, there could be, in this case, there's 600 meters from the outermost source to the outermost streamer. The problem is illustrated here. This is a lack of near offsets. We have here a conventional acquisition, a source and a streamer behind it. There could be 200 meters, perhaps 150 meters between the source and the beginning of the streamer. And when we shoot seismic, we only, for the shallow reflections, only record a small portion of the reflected wave field. Because as shown on the little sketch on the lower right there is a maximum angle of reflections that you can actually use. So only the green energy there shown on this map can be actually acquired. So let's look at the concept of shooting over the spread, some of the characteristics. You see on top aerial view of a conventional acquisition, and on bottom shooting over the spread. The characteristics are, the most important is we have sources on top of the spread. And by that we get 0 offset, and we also get a split spread. We get energy going both forward and backward on the spread. We have a wide tow sources. We spread them out, unusually wide. That means that the distance from the outermost source to the outermost streamer becomes quite small, and that is a very good thing. That means we can reduce the minimum offset. And the third thing is a dense spatial sampling. And that also increases the subsurface illumination, and it also reduces the minimum offset. The concept is called TopSeis, and we have been working on this, as I said, for several years. So the TopSeis, as opposed to a conventional acquisition, has sources on top of the spread, as shown here. When you shoot the same cone of energy into the subsurface, we record all of it in the streamers. So when we look at a coverage, a near offset coverage, this is around 200 meter offset class. On the top you see a conventional acquisition, and the bottom you see the TopSeis acquisition, where the blue dots indicates midpoint positions or coverage. As you see, it's very difficult to build up an offset class on the conventional one with such a sparse acquisition or a setup, whereas TopSeis has a coverage everywhere. The TopSeis technology was created based on the challenges in the Barents Sea. There are serious imaging challenges in the Barents Sea with the current technology. Here we see a random line, a seismic line through the Loppa High area in the Barents Sea, with the 4 discoveries and prospects that are all located in the Permian carbonates. They are all located very shallow, less than 2 seconds, and they are located in a very high velocities. And that's a problem. That means that the need for the near offsets that are a key part of TopSeis is particularly important in this region. If we zoom in to the reflection at the Permian carbonates, you can see how the rays bend, and that creates a very small maximum offset that can be used. And the various maximum offsets for the 4 discoveries are shown from the left to the right in this Gohta discovery, Alta discovery, Lundin discovery, and Reservoir prospect. This lack of near offset in conventional acquisition has been a big problem, created difficulties in seeing clear images in this area. So TopSeis was one attempt to improve this situation. We'll see soon how the data looks like in this area with TopSeis. So before that, we just look at the data from TopSeis. This is the shot gathers from a field test we did in the North Sea in 2016. On the left, it's a TopSeis shot gather. On the right, a conventional gather, with a cartoon showing the geometrical setup. First of all, we need to mute the data. These are the data that we're muting away before we start to look at them. And only and if you look at the water bottom reflection here and here, you can see there is only 1 or 2 traces on the conventional, and there is a lot of traces, like 10, 12 on the conventional. You can also notice the upgoing primary energy and the downgoing ghost separating in TopSeis, whereas they are together in conventional acquisition. Here's another shot gather from offshore Gabon, where you have a conventional on the left and TopSeis on the right. You see some of the characteristics of TopSeis. One of them is a direct wave, which is quite strong. It's so strong that you even get clipping on the very nearest hydrophones. You can see the propulsion noise from the source vessel, and you can see the separation of the source ghost and the upgoing energy and the downgoing energy, and that's ghost. On the conventional, you can see you don't have a lot of this, but you have a lack of near offsets. So another aspect of TopSeis I'd like to describe is the noise level, because noise is a problem in all seismic acquisition, including conventional marine seismic acquisition and TopSeis. So we have the question here, where is the ambient noise strongest? In front of the cable or in the middle of the cable, where the sources of TopSeis are located? Here we have noise records from the Barents Sea. That means we were not shooting, we're just towing the 14 cables with the source vessel just floating over. And you can see quite clearly on that zoom that the noise is stronger in the front. And we're now going to compare the noise in the front of the cable, that's the green curve, and the noise on the center of the cable underneath the source, that's the brown curve. And we're looking at the frequency spectrum of these two, and you can see that in front of the streamers, where you normally acquire your near offsets, your noise level is considerably higher than in the center of the streamer. Another aspect, when you are shooting on top of the spread, You're also able to correct the small errors in receiver position. All receivers have errors to them, particularly in the middle of the cable. The end of the cable your navigation is the GPS. In the middle of the cable there's a acoustic pinging system, and it has small errors. With TopSeis data we are able to correct for them. On the left here you see before water bottom from before correction, and the right is the water bottom after correction. And the way this correction is done is to look at linear move-out plots or linear move-out data from the direct wave to the channel. And the first event that you see here, the little jittery event you see there, is supposed to be flat if the position was right. After the correction, we are looking at the same QC, and we see now that the common channel gather is straightened out. Even the water bottom is improved. So we are able with TopSeis to correct data that would otherwise be uncorrected. So I'm going to describe some of the results and also some of the process that led to this TopSeis that we're working with today. We started 4 years ago, 2014, with modeling and some testing. In 2016, the first field tests were done. First a 2D in offshore Gabon, then a full 3D mini survey in the North Sea. And then last year, the full-scale Barents Sea survey was done that you saw a picture of earlier. Let's look at the Barents Sea. That's the most recent and the most interesting, I think. So Barents Sea is, of course, the sea north of Norway. And we did the full 3D 2,000 square kilometers acquisition in the southern part of the Alta-Gohta area on Loppa High. Then we went up to several 2D lines and also did a small mini survey up in Wisting area, far north. There's also a discovery by OMV. First, we're going to look at the Loppa High. Here is a vintage. It's an inline, and it consists of several vintages of seismic data. So this is what Lundin have worked with up to now. And we now compare with the preliminary processing of TopSeis data, and we can compare those two. And you can see there's a striking difference, both in resolution, faults, even down at deeper levels. Even and the deepest part of this seismic is like 2.5–3 seconds, and even at those levels, TopSeis is considerably better. It has met the expectations so far. So let's look at the Wisting. Wisting is an area in the north operated by OMV, which is going to be developed as an oil field. What we're looking at here is a historic moment in Norwegian history. This is when Amundsen and his men were the first to reach the South Pole in 1911. The reason for showing this is that Wisting is one of the expedition members who was present on this expedition. So I guess the big find will be then called Amundsen field, probably. But we're going to look first at some examples from the processing flow of TopSeis. On the right here is the processing flow. We're not going to go into detail on that, but the processing essentially means that you're taking data that are not very good initially in terms of noise and multiples and ghosts and all of that stuff, and you're trying to work with it, process it, and image it to get a good image in the end. We can look at first how the data looks like raw. Here we see the raw data. On the left, a CMP gather. On the right, a CMP stack. We're going to see how this data evolves through some of the key steps in the processing. And here is the data after deblending and after deswell. So we're going to move to the next one, which is after the deghosting. So now we're looking at the receiver deghosting and flipping back and forth. And we can see how the ghost, that is the ghost of the energy going up, is removed. So the next step is after source deghosting. So here the little white event after the main events are gone. And then after demultiple. It's an important step, which removes that curtain of energy that you see down there at around 1 second. This is where TopSeis has a big advantage because it has the access to the near offsets. Finally, the final image, the final migrated image. You can flip between that as well. And we can see all the triplications and all the diffractions are then collapsed into the nice image. So now we're going to look at the AVO on the Wisting area. Shallow AVO. TopSeis is rich in near offsets. It has a dense illumination, both for near and far offsets. So TopSeis should be good for AVO inversion. On the lower sketch there, we see what an image gather looks like and the AVO extraction would look like for conventional acquisition. And this is a TopSeis acquisition to illustrate that point. We did also tests before this. We did modeling studies. And this is a modeling study from 2015 where we investigated both imaging as well as AVO. On the right there, you can see the truth, because in modeling you know the truth. We have the oil-water contact gradient G volume that's been extracted on the lower right there. And on the lower left, we have the conventional value of G. Very difficult, very noisy, very difficult to see similarities to the image, the true image to the right. The TopSeis image in the middle is much clearer. Not only the imaging itself, but also the AVO is much clearer and more consistent with the truth. This is very convincing, and we did this back in 2015. So the results we saw now that I'm going to show you are not going to be a big surprise. So this is the central well in the Barents Sea. This is the discovery well. You can see the water bottom there. You can see an inline. You can see a cross line. And the top stø is the reservoir rock, the reservoir layer. So we see again an inline through that well, and we can see the top stø where the oil was discovered, and there was an oil field. So AVO require knowledge of the various amplitude of the various angles, and here we are looking at an image gather where top stø is indicated. We can drape the reflection angles on top of that, so you see angles on both sides from 0 to 40 degrees. And we can look at the gathers when you mute the data that you need to do before you use that, or before you also use it for AVO. We are now, just for comparison, I'm also muting the data that are not visible or present in conventional acquisition. And you can see it's only a small 3 or 4 traces in a range from 20 to 30 degrees that are usable for AVO, and that's not much. So we're going to look now more at the reservoir. On the right there, you see some well measurements. The resistivity on the right is very strong in the top stø level, showing that there are hydrocarbons. And the gamma ray shows reduction and a very stable value of low values, which indicates clean sands. So top stø is what we're going to look at. Here is the yellow line here indicates the top stø interpretation. So it's a very irregular reflector. It's in faulted Permian blocks, and it consists oil on the top parts. We know there's oil there. Here we see extraction of the amplitude along the top stø horizon that you saw on the previous slide. You can see that there is a strong negative anomalies on the top of the structures, indicated in red there. But when we look at the wells, we know that the well on the right there, the Wisting discovery well, was finding oil. We know that the Hansen well, the one on the left, also found oil, and we know that the well there in the third well there was dry. But based on this data, it's not easy to see why they were dry until you have the AVO. And here we see the AVO product R0 times G extracted around the top stø horizon. We can see the 2 discovery wells and the dry well indicated. And it's a remarkable consistency. I mean, both discovery wells are in areas of type 3 AVO, which is an indication of hydrocarbons, whereas the dry well is in this green area where there is not a type 3 AVO. To get a bit more confidence in this, we just wanted to put on the high isochrones. So we're now looking at the isochrones in these faulted structures, and we see how well they are consistent, how well they follow the AVO anomalies, which indicates that these AVO anomalies are gravity driven, that they are liquids and gas that are sitting on top of the up-down structure, which is the reservoir. So finally, I'd like to give some conclusions on TopSeis. It provides unique illumination and fault for improved imaging and reservoir characterization. We have shown both examples of imaging and reservoir characterization in this talk. We have done a comprehensive verification, not only on the modeling, but also field test program, and also taking all HSE aspects into account. The first commercial survey was done in 2017, and we have shown examples of that. The results are very good. And finally, this project would not have been possible without this close cooperation between a cross-disciplinary team of experts from CGG and Lundin. And finally, acknowledgement of a lot of people who were present or worked on this project for these last few years. Thank you very much.